Hey, um, I guess I'll put my face over there. Well, this homework assignment was way too much. It took me about, yeah, it took me like an hour and a half, which if it takes me an hour and a half, a stat student, I don't even know. That's a long time. Well, for 7.1, we took the population mean and then the standard deviation that was provided in the book in exercise 7.1, and we graphed it. And this is just like what we had when we were working together earlier. He also said in the lecture that you had to make a histogram as well. So in the homework on D2L, it says to sketch it. In the lecture, he said to make a histogram. So this histogram was done by entering all the data, the raw data that was in the book, so all those numbers. You highlight all of those numbers, all of them, and you hit insert. So let me do an example. Insert this histogram button, insert statistics chart. It will give you a histogram, and click on that. So after that, it gives me this histogram, and we have to change the bins. So if you double click on the x-axis, so wait till it says horizontal axis, double click on that. Go over here to this format axis column, and go to axis options, this green bar chart, and click on bin width. And as he said in the lecture, the bin width needs to be 1.25 so I think the default bin width is something like 2. So it might look something like that. Need to change it to 1.25. And then I changed the title of it to histogram for 7.1. We can call it 7.1 data. And yeah, it was a uniform distribution. So it's supposed to look like a uniform distribution. Yeah. That's weird. Hold on. I guess that's fine. It's supposed to be flat. So they take this, I don't remember what page it was on, but they take all these numbers and then 5 at a time, they sample them. And I have beef with this homework problem because you're supposed to create a sampling distribution, and a sampling distribution is theoretical. So that's why I got confused. But he wants you to make a sampling distribution based on real samples that were provided. So I redrew the distribution, copied it over here. My mean was gathered from the data. So I took all the sample means that's in the problem 7.2, and I put them all in, and then I did the population variance and so on for that. So subtracting the mean, and that's confusing. Call it, it's just x. Subtracting the mean, squaring the deviation, and then we get our statistics here. So first of all, you have to make a histogram once again, and this time with the sampling distribution. Now, you highlight all those sample means that were in the book there in 7.2, and then once again, go to insert, histogram, this one right here. I'll do this one for example. Oh, okay, never mind, I don't like that. Let's go back to that. I don't know what that is. So we get our sampling, I called it sampling distribution, and then double click on the horizontal axis once again, over to the green bars, over to axis options, and then our bin width is once again going to be 1.25. So going through this, going rather quickly here, but that's spelled wrong. Distribution. So I have here mu, and mu was gathered by yeah, he said to get a mean in the lecture. So I got the mean from the lecture, or I got the mean from the data. So the mean is 4.45. I put it up here. I'm a little confused on this because the sampling distribution is supposed to have a population mean in the middle, but oh God, I just don't know. I'm really confused on some of these problems. But if we wanted to, we could make it 5 for the population mean. What was the population mean? It wasn't 4, it was 4.5. And then it would change these ever so much. What is this? Yeah. But because the population mean is supposed to go there in a sampling distribution, but he said find a population mean, so we found this. We found this when computing. So I'm not sure if 5 is supposed to go there in 4.45. I'm not entirely sure. Population standard deviation, though, that's correct. He wants that number right there. The average of these squared numbers, otherwise known as a mean square. It's population. Oh, wait. No. I'm talking about population variance. No, we need excuse me, population deviation. So population standard deviation, which is the square root of the population variance. That's 1.19. So that goes there. And then our standard error is here. That standard error, let me make this smaller. That standard error is just the population standard deviation divided by the square root of K3, which is 5. Because he said to use an N of 5, because since we're making a sampling distribution, we're using the N of every sample. So every sample has an N of 5. This was blowing my mind because we're mixing theory and application in a way that it's not supposed to, but it's for the sake of demonstration. So it's extremely confusing as somebody who didn't learn it this way. He had just recently started teaching it this way this summer in a different class. All right, this is the homework. Well, it's all the homework, but this is the 7.6. For some reason, on D2L is just a mistake. He put 7.3 as the homework, and that's why I was so freaking confused. It's 7.6. He said in the lecture the homework was 7.6. He was even going over it to preview it a little bit. So this is 7.6. If you look at 7.6, it's testing the Dunning-Kruger effect. If you're not familiar, the Dunning-Kruger effect is that people basically have an attitude, or they have this presupposition that they have a higher aptitude among some domain than they actually do. And the people that are subject to this fallacy are usually people who are laymen's, and they're laymen in terms of the domain that they're trying to judge themselves within. So in this example, we were talking about some test scores, and they took 11. I want to say, first of all, this is an extremely difficult, this is a really advanced problem to do a one sample T on in terms of like how the research is a far interpretation of the data itself. I mean, if you're teaching a one sample t-test the very first time, I think it's better to have something much more simple. But on the other hand, there's a lot more room to, I mean, for brilliance if you like give somebody a really hard question, I guess. But in this example, there was uh, this test, the standardized test, and on the standardized test, the average was a 50. And that's not a raw score, that's a percentile. So what we're comparing the students scores that they thought they got to, we're comparing it to 50. It's a really complicated problem. It's just complicated. But these 11 students, they sampled them because they scored in the lower 25 percentile. So 100 people take this test, these people would be the bottom 25 people in terms of how they scored on it. So that's setting up the Dunning-Kruger effect. We have the people who are the least skilled, and we're testing that, and we're also testing if they're unaware. So how we're testing they're unaware is we ask them, what score do you think you got on this test? So this list of X's that we're calculating is the scores that they thought they got. So for example, this 40, this person thought they scored in the 40 percentile, better than 4/10 or 2/5 of everybody, but they actually scored in the bottom 25th percentile, so the bottom quarter. All these people scored somewhere in the bottom quarter, but they think that they did much better. So these are the scores that they think they did. So what we're doing is with this one sample t-test is to see if these people made a false evaluation, self-evaluation, that they had scored significantly better than average. And the Dunning-Kruger effect expects that they think they scored significantly better than average because they didn't, because they scored very low. So you hear Dunning-Kruger a lot, but I hear it the most in like medical field, where, for example, there might be like you're talking to your doctor and your doctor is explaining how you should change your diet, but you read like 2 weeks ago in Reader's Digest that this specific diet works really well, and your doctor's like, no, it doesn't. And then you're like, well, I know better than my doctor. That's the Dunning-Kruger effect. You don't know as much as your doctor. You could be right, but that's irrelevant. You don't know as much as them, but you think you do. It's a very good thing to be aware of. That's what this is testing. I hope that explains it well enough. So these people scored in the bottom 25th percentile. They asked them what they thought they scored, and we're trying to figure out if they thought they scored significantly better than average being the 50th percentile. That's where our population mean comes from, is the 50th percentile. The N is 11 because there's 11 students that we're testing. And the standard error is the standard deviation, which is the sample standard deviation that we got from our scores. And we divide that again by the square root of N. And I've highlighted N here. So I've highlighted sample standard deviation and N. So that gives us a standard error. So now that we have the population mean and we have the standard error, we can graph the t-distribution, or better, the sampling distribution. So we start at the mean, and then we add, you can see I added the standard error every time, so 6.86. This is 50 plus 6.86 is 56.86. And then 56.86 plus 6.86, again, is 63.72. And then we go that way. And then we subtract 6.86 going this way. Same thing here, we start at 0, we add 6.86, 6.86, 6.86. and then we subtract going this way, and then we just have our t-scores on the bottom. So 1, 2, 3, 1, 2, 3. That's all. It's always 1, 2, 3. Starting at the research question, our research question, it's right there in the book. That's not, don't try not to overthink the research question. It's really just exactly what you're trying to find out. So, are the students unskilled and unaware? The research questions are identical whether you're doing a two-tailed test or a one-tailed test. So I've done both here because that's the homework. You're supposed to do both. For number 2, we have our symbolic. So you need to use the mu symbol and the X with a line drawn over it if you can. This is just so I could save some time, but he'll want the symbols in the homework. For a two-tailed test, it's either equal or it's not. The null is that it's equal. The alternative is that it's not. For a one-tailed test, it's a little more complicated. The null is what would be indicative of you not finding what you think you're going to find by means of testing one tail. So the null hypothesis for a one-tailed test is that the average that the students thought they scored would be less than or equal to the actual average. So that's testing. We would have a null finding if it were equal to the mean or to the left of the mean. The way I do it, or the way I started off doing it, was for a one-tailed test, I would start with the alternative hypothesis, because the alternative hypothesis is what you expect to find. And if you outline what you expect to find, then you can just by default know what you don't expect to find. So we expect to find that the students will estimate that their scores are greater than the average of everyone else's scores. So that's easier. And then for the null, it's just not that. It's not what you expect to find. It's a null finding. Some of this might be explaining too much. Some of this, yeah, I'm just trying to hit it all. And I've battled back and forth of whether you should change the verbal specific within context interpretation of the symbolic hypotheses based on whether there's a one or two-tailed test. But I've concluded, I hope I'm not wrong, but I've concluded that we're still trying to find the same things in the research. So we're still trying to find that the students accurately estimated their scores, or they thought their scores were higher than average. And then so a null finding would be the students aren't deluded and they are exactly as smart as they thought they were. So it would be null if they expected to get in the lower 25th percentile because they actually got in the lower 25th percentile. So that would be null. That wouldn't explain the Dunning-Kruger effect like we're trying to do. Hold on. Okay. I want to make sure my microphone is still going. And I don't know. I mean, you could, I really think it's up for debate. But you could say different. This is very conservative because the students thought their scores were different than average. So if X bar doesn't equal mu, it doesn't mean it has to be larger. It doesn't mean it has to be less. It's just different. So I don't know. That's more Dr. Hamlin. That's more what statisticians begin to disagree on, I think. So for the standard error, this is the base equation, x minus mu Let me fix that, x bar minus mu over the standard error. I don't know if you actually need to put the equation and all the symbols and everything. I just did that for example. And the calculations are identical. 67.91. So the sample mean minus the population mean of 50 equals 17.91. And then the standard error is the sample standard deviation divided by the square root of n. Did that on both of these. Got the same test statistic. However, the t critical value is different. And you get that t critical value by looking in the book. It's on page 702. So where I got 2.228, I went to, it's going to be hard to read, level of significance for a two-tailed test, and then it's 0.05 because we're doing a two-tailed test. So we go to the two-tailed test line, 0.05, and then we scroll down to the appropriate degrees of freedom. So that's going to be, sorry about my fingernails, that's going to be 10, 11 minus 1. So go to 10 and scroll all the way over to where we have significance for a two-tail, 0.05. It's really hard to read backwards. And then that'll be the critical value. And for the one tail, you go to 0.05 right here for the one tail part, and then line it up with 10 degrees of freedom again. That's how that's read. It took me like 2 years to read that thing easily. It's hard at first. And then we get our p-value, and the p-value is the t-dist formula. We put our t-value right here that we got, 2.61, our degrees of freedom, 11 minus 1 is 10, and then our tails, this is a two-tail test, so we put 2. So that's our probability using a two-tail test. For the one-tail test, just put a 1 there in the end instead. And that is half. So yeah, the two-tailed test doubles the probability because we're testing both ends. So I put the critical value of at the 0.025 level on both tails. I put the critical value at the 0.05 level on the one tail, and we're testing the right tail because we want to see if their scores are significantly higher than average. So we're testing the right tail, and that critical value, as we saw, was 1.812. And then I labeled the t-value that we found. I labeled the two-tailed p-value. Yeah, I think that's okay. You could put two-tailed. It'd probably make more sense to put the one-tailed p-value. Yeah, I don't know. We prefer two-tailed most of the time, psychology. So we're just gonna go with that. Okay. Yeah, this homework is too much. I gave like 2 assignments, in one day. I don't agree with that, but I hope this helps. I hope I guarantee that the other students are not going to turn in something like this, so don't sweat it too bad. And also, please seriously, don't like replicate this, because if both of you turn in something that looks exactly like this, like formatted the same way, obviously you want the same numbers, but like formatted the same way, these lines are drawn the same way. Um, yeah, he'll know you went to SI, but then it's like it's just copying. Uh, that's not good. He doesn't like that. I don't like that. It's awkward. Okay, guys. Thanks. I'm really sorry about this being new to me, some of this stuff, or at least being confusing to me. But I hope this video helps.